already, and they're going to be starting on. They started in Oh.
Well, welcome back, everyone. Looks like it's time to get started. After the conclusion of this class, we're 25% done. This will be the end of week 4, so congratulations, everyone. Just 75% more to go. Any questions at all to start us out? Okay, definitely we probably want to talk about some announcements, so let me click on this screenshot here. So we're in section 1.8. We're moving forward into new content today. Although this new content is not on exam 1. This is the start of the content we'll see in the next upcoming exam. But the good news about the content that's right here is it is an introduction to linear transformations, which also means we're doing quite a lot of stuff in those sections already in that section here. So it does contain a good amount of review topics. Aside from that, our first exam is going to be next Tuesday, like we discussed. Don't forget to bring a calculator. I'm not designing problems that absolutely needs it, but if you maybe just need a calculator for extra comfort, reliance on the exam, that's completely understandable. It's only going to go up to section 1.7. And here is the sample review problems. I guess we can click on the real thing. These are just the old lecture notes, and also any problem that came from your homework would be considered a decent exam problem. As another reminder, this is included on the exam itself. Our exam is closed notes, closed book, but there's always going to be formulas that's attached to the last page of each and every exam. And for this exam, it's going to be these two theorems. This one is one we used all the time, but what the heck, we had a little space here, so I threw it on there. But this is the bigger one. This will probably be, I'd say, at least 2 questions on the exam could be directly solved by just looking at that theorem and connecting different aspects of the question. So that's what we're going to do next class when we come back on Tuesday. Any questions or comments at all, folks, before we get started? Okay, well, let's take a look at what we're getting into in section 1.8. After this section, we'll have one more for chapter 1. Then we'll be moving into chapter 2, doing some matrix algebra next. But in 1.8, this is a pretty exciting section for linear algebra, because I feel like this is the first point in the course where we can properly define what we even mean when we say linear algebra. We definitely don't mean this.
I have a quick question.
Yeah, go ahead.
You probably stated this already, but I joined a little late. What sections is on the exam?
You can find it right here on the Moodle website. They'll go from 1.1 to section 1.7.
Oh, perfect. Thank you so much.
You bet. And definitely check out these 2 documents. These are the review problems, and all of your homework problems are great review for exam 1 as well. And this is the sheet that'll be attached to the last page of the first exam.
Oh, perfect. And you said that there's about 20 questions?
It's going to be 20 questions, yes.
Thank you so
It
much.
sounds bad at first, but it's actually not as terrible as it seems. Other questions at the moment? Thanks for asking about that on the exam. Okay, well, let's go to our 1.8 document. And again, linear algebra is kind of a weird class to sign up for because its namesake makes it seem like you're doing this, right? There's your linear equation. And in some sense, we did deal with that. We wrote out, by definition, some linear equations in multiple variables. But I'd say the better definition of linear algebra is this, linear transformations. A linear transformation has a domain vector space and range vector space as well. And so this is really what we're doing in the study of linear transformations. And when we say linear transformations, let's include just a quick comment right here. We don't mean this. This is just the definition of our new set of functions from a vector space into a vector space. This does not define a linear transformation at all. This is just a generic one. So let's just say here, just as a mention, this does not define linear, at least not linear in the meaning of linear algebra. But we're getting started. So now we're going to begin developing functions. In a certain sense, we've already been doing that throughout the course, but we're formalizing it. A transformation could be referred to as a function if you like, that's completely fine. It really is a mathematical function. It passes the one-to-one, or not, excuse me, not one-to-one, but it passes the well-defined nature of actually having a function. You could call it a mapping, and you're all always referring to the same thing. We'll have it map from Rn to Rm, and we can indicate it by writing that out in this kind of way. For example, here, we're mapping from R2 into R3, and it's defined by doing this. It takes a vector of 2 elements, so there should be an x1 and an x2 that shows up here. And it outputs a vector in R3, so it should have 3 elements. And here it is, 3 different rows. One of them is always 0, but that's okay. That's our generic linear transformation. So when we go to define these things, if we say we're going from Rn to Rm, Rn is going to be the domain, Rn is going to be the codomain, and I notice I dropped some color coding here. There we go. And we can indicate domain codomain by using that notation right there. So this says T is a mapping from domain to codomain in that way. Other notations and terminologies you'll see in this section quite a lot is, if you take a vector x and Rn, T of x is what the author will call the image under the action of T. And the set of all images, all the potential outputs of that transformation, is what we think of as the range. The range is important, but typically in linear algebra, we focus a lot on domain and codomain. The range is just contained inside the codomain, and it could be in the entire codomain itself. That's a lot of verbiage there to start us out. So on this problem right here, we have transformation from R2 to R3. I like to write them out this way, and the author sometimes does as well, but occasionally you'll see this same transformation indicated this way, kind of a sideways notation. So x is a vector of elements. When you see that x there, think of x equals x1, x2. Then this whole thing, we just wrote it in sideways, comma separate it, and you're really saying the same thing. Our author does this sometimes to save pages on your book. So if your book was just a little bit cheaper, because this takes up a lot of vertical white space. So sometimes it's just a notation to compact things down. I think this is better to study it this way in linear algebra, but it's important to see it both ways because that's common notation as well. That's a lot of verbiage and definitions. Any questions at the moment? Okay, let's take a look at this question. It says, what is the image of x? X is 1, 2 under the mapping T. This is some terminology you'll see a lot in the homework. Image of x. All they're asking you to do is this. We're just calculating T of x. So that's a weird way to indicate it, but this is common terminology in linear algebra and other branches of mathematics. So not a bad time to start picking up those kinds of terms. Well, to do T of x, another way you can think about it is it's the same as taking T of x1, x2. We know the values of x1, x2. It's going to be 1, 2 coming from here. So we have T of 1, 2. Then our output after doing this evaluation, and notice the notation is clunky. This is the vector x, but in function notation, we use this to say of that vector. But now that we have this, x1 is going to be the value 1, x2 is going to be the value 2. And we just plug them in here and to the right corresponding positions. It's honestly a little bit tricky. You have to follow your eyes or your fingers carefully to make sure things are dropped in the right location. So to start this off, we'll have 2 times x1, so that's 2 by 1, minus x2. x2 is the value of 2 down below. Then on the second row, doesn't matter what x is, we're just going to take a null element there, so 0. Next one says 5 by x2, so 5 times x2, which is 2. And I don't know why I shoved things so far to the right. Let me drop it in quality down here. We're pretty much done. We have 2 minus 2 in the first row, first entry for a 0, then a 0 and a 10. So when it's now asking for the image of 1, 2, under the mapping T, that's all fancy language to say, just do this right here. How do folks feel about that? Does that make sense? Awesome. Just an ordinary function evaluation. It just happens to be that it's a function of 2 variables going into 3-dimensional space. Kind of weird, but same kind of process for function evaluation. Well, after doing that kind of stuff, I'd say the most important part about example 1 is just recognizing when they say image of X. This comes up a lot throughout the exercises and problems we'll see here. Any questions at all, folks, before we try the next? Okay, so we've got a notion of what is a transformation. We still don't know what we mean by linear. We've yet to define that, but we're getting closer. In fact, we're just about there. Here it is. I never used this theorem directly when we were in section 1.4 because we never had a cause to use it. So I decided, let's just ignore it until it's relevant. It's here in the notes in section 1.8, where we're really going to use this theorem. The theorem says, if you have an M by N matrix, so M rows and columns, and you take 2 vectors from Rn, a generic scalar, then these are 2 properties that matrix multiplication does satisfy. It has a distributive law. So we ought to expect that real numbers have a distributive law, and that's how you prove this. You just use the real number system. And this is a kind of quasi-commutative property. The scalar here, well, you could scale U first and then take A times the result, but you can change this up. You can, in fact, take C, put it for to the left, and do A times U first, and then scale it by C. You could do that in either way. So it's a sort of commutative property where C has commuted in front in that way. So those are some nice algebraic properties. They didn't seem like much, but now they are extremely relevant. Here's how we define a linear transformation. And it can be from any kind of vector space. It just says for vectors UV in the domain of T. Our vector spaces can be pretty strange. Sometimes they could be function spaces or even more exotic. But if we have this property, then, well, that's just always a helpful property. And this one as well, it matches up with this one. If your transformation always does that for any pair of vectors U and V and scalar C, that's when we say your transformation is in fact linear at that point. And throughout the course, we'll be discovering more and more properties of linear transformations. We won't do a lot because this is not an advanced course in linear algebra, but it's a good place to get started in this class. Well, any questions, folks, about their definition here? Okay. Well, this definition, together with the prior theorem, is going to give us an entire class of functions which turn out to, in fact, be linear. But let's start with this one. We're going to go from Rn into Rm. So that's how we define domain, codomain. It's defined by that formula there. So T of X is just A times X, where A is that matrix here. Inject a little bit of space. They ask us to start off, what is the domain of T? It's right there, but the question is, what is the N there? Is it R2, R4, something else? It's kind of a tricky question, but let me show you how I would get started. You want to put right here the size of the matrix A. Would you call that 3 by 2 or 2 by 3? Exactly. This one has 2 rows, 3 columns, so we have a 2 by 3 on this one. So let's put in 2 by 3 for A. Let me see if I can fit that a little bit better just to make it noticeable. So A is of size 2 by 3. Now that says something specifically about X. We're assuming that this matrix times a vector is defined, right? So X has to be of size 3 by 1 for this to make sense. We just use the arrow strategy. That's of size 3 by 1. And this far into the process, we'll be able to identify what goes into the superscript for Rn. Anyone spot what it should be? Is it the 2 or the 3? Anyone over Zoom spot, which it should be? Should we say this is R2 or R3? Turns out this one is not R2. And it's kind of tricky though. One way you can connect the thought is the moment we said A times X, it has to be defined, right? That means we had to take this. We knew it had 3 columns, but we also know there has to be 3 rows in X. But X comes from here, Rm. So that means this should be R3 right here altogether. One way to think about it is if A is a 2 by 3, this 3 is what you form for the domain. Our domain is R3 on this one. And notice how uncomfortable it is. It switches on us. I would like to say 2 to 3, but it's actually R3 into R2. It's a consequence of how multiplication is even defined here. In fact, we can go even a little bit further. If we say, let's use a different color pen. If we say that this is equal to B, so A times X gave us another vector, the size of B would be 2 by 1. But B, where does that go? It's an output. It means it goes into the codomain, goes right here. And so this should be R2, matching up with this. So the codomain is R2. The domain itself is R3. I think it's tricky to track. It's not something that's terribly difficult to memorize, but in exam, it's easy to get stressed out and forget which way it goes. So to track this really carefully, you could do this kind of color coding. For this value here, it came from X, where X was the input into the function. And that's why we have a domain right there of R3. And for M here, the codomain, that's just the size of a resulting vector. It'll be of 2 by 1. So the codomain is R2. In other words, take this 2 by 3, switch it. We're going from R3 to R2, and that's a decent mnemonic for this. But if you ever lose your way, pretty much writing this is how you can always recover the way it ought to go. This is maybe even more important than mnemonic.
Why do you have B versus system matching?
Yes, exactly.
One?
It came from there, exactly, yes. So whatever these 2 sizes happen to be is the right size, exactly. If it was a 2 by 5 for some weird reason, that'd be now a matrix. We would have 2 by 5 here. Does that make sense to folks so far?
How did you get 3 by 1?
Oh, the 3 by 1 right here? Well, we knew that X had to be a column vector. So the 1 is going to be the number of columns inside of it. But also, we were mostly looking at the size of the matrix A. A was of size 2 by 3. And so if it multiplies a vector X, these 2 dimensions right here, let me move these things. This one and this one have to match up. So we just dropped in a 3 to make multiplication actually compatible. Does that make sense with that 3 there? Awesome.
X that is the X always going to be called vector, will always be 3 times 1, 8 times 1, but always in a single column.
Yes, absolutely. In this context where you have a transformation T like this, that is in fact how it's always going to go. Absolutely. The only way I'd have to change that up is you'd have to change up the vector spaces, but we're keeping it just like these, not anything weirder or such. Other questions about that so far? Okay, those have been great questions. And that's one thing that's kind of tricky about this is unpacking all this algebra. It's hard to see at first, but once you delve into it more and more, it becomes not as bad. Here's the next big part. We want to verify that this transformation T is linear. Now, if you've taken some math classes, proof-based classes, you might have decided, well, I know how to prove linearity. Just take an arbitrary set of vectors u and v and show that this holds for our specific transformation T using that matrix. Then we would pick an arbitrary vector u, an arbitrary scalar c, and show that this holds. And that kind of proof does work. And You would get the same amount of credit as everyone else. It's a lot of work, but it's pretty awesome to know how to do that. However, you could just use this. We're going to prove linearity by just taking advantage of some algebra we know about a matrix times a vector already, without having to reverse engineer this kind of stuff. But we will be looking into this a little bit more closely down at the bottom of the notes when we're trying to show a transformation is not linear. It means one of these two properties would have been broken, and we'll be looking for a counterexample on how it broke. So to show t is linear, we just have to observe since t of x equals ax for all u, v in, so I'm picking arbitrary vectors u and v in R3, they have to come from the domain, and all scalars C, sometimes the author calls these weights instead of scalars, but they are always in R, any arbitrary real number. Let me zoom out just a touch to try to fit this in. First thing we're going to show is this property will give us this property. All we have to do is take t of u plus v to start. Now we have to look at what does t do? It multiplies a by whatever your input happened to be. So if you put u plus v there, it'll go right exactly here. You'll have a times u plus v. But the moment you write that out, we can use this property, distribute a into the vectors, you'll get au plus av. And now at this step, we're reverse engineering this. If you have an au, it'll turn into a tu right here. So from this portion, using the mapping going backwards, just put in a u in this position. Au turns into t times u. So that takes care of that one there. And same thing with this one. If you have ax turning into tx, well, av here will turn into t of v. So t of v is a better way to say it. And notice we just showed that first property does indeed hold. We just kind of powered through it by using known properties already about matrix multiplication. Now we just have to show this property holds. Well, any questions so far, folks, about that first run through on this one? Okay, let's maybe pause on that first one and show what in the world did we really do? This says, if you want to take a mapping u plus v, you have options. You can do the vector addition right here, or you can do the vector addition over here. This is wild because vector addition right here, coming from that vector space, could be totally different than the vector addition right here. That could be a function space or something more exotic. They don't have to be the same kinds of vector spaces necessarily. So what we're saying here is you can either add up the vectors in your domain, add up the vectors in the codomain, and it makes no difference. This is called operation preserving. It didn't matter where we did the operations. You could do it in the domain space or the codomain space. You get the same results if t is linear. T is nonlinear, anything can happen. Those functions are the weird ones, the ones you study in calculus, the weird curves and such. But linear functions are extremely rigid. This is a property they will always have. And same here, you could either do the scalar multiplication in the domain space, or you could do the scalar multiplication in the domain space, codomain space. It preserves that operation as well. Now let's show this one holds. The other questions or comments so far, folks? Okay, I'm going to need this part of the theorem, but we're also going to need to scroll, so let's just dump it right here for the moment. Kind of hard to show everything all at once, but I think that'll work. There we go. So second thing we have to show is, this is part I for the definition of linearity. Let's go to double I. And we'll take, well, we already defined a vector u, which is arbitrary, a scalar c. We can consider these vectors in the same scope of our next statement right here, but we only need one. Take t of c times u, Now let's go and say what the mapping T does. Whatever's inside here, we just multiply by the matrix A. So this is A times the scalar multiplication C times U. But now we come down here and it says, if you have A times C times U, then you can just rearrange that scalar, put it way out in front. We'll do exactly that. Here's C times A times U. Let me redo that color coding. Now we are reverse engineering a U. That's much like this, but you're putting a U inside here for T like before. This becomes, let me try again, C times T times U. So that means this property did indeed hold. And we know it should have. We were just showing it explicitly using that property down below. The vectors U and V were completely arbitrary. We had to show it works for every single vector in R3. That means you can't actually pick an example here. It must be arbitrary. And same for the scalar C. We can't pick a value of 5 and show it works, because it also has to work for 50, 50.3, or all that kind of weird stuff. So we have to work completely arbitrarily in this way. It's a little bit wild, but what we didn't do was use the generic matrix. We used those properties. That's what made it so much faster, and that's what I encourage you to do. Well, any questions, folks, on getting through that one? Okay, it turns out that matrix is not special to this. Anytime you define a transformation in this way, your transformation is in fact linear. So that's a wonderful property to have. And it also means all of those matrix multiplications we did, starting in section 1.4, we were in fact doing linear transformations. We're just adding the notation and vocabulary on top of it to describe a little bit better what we were really doing in all those prior sections. But let's keep on going and see what else we're getting into. Any questions so far, folks? Okay, let me get rid of that temporary screenshot there. And this theorem kind of just defines or says what we were saying before more explicitly. If your transformation goes from Rn to Rm, but it's defined this way, where A is an m by n matrix, notice the m here, this is worthy for color coding. This m right here goes to the m over there, and the n right here goes to the n there. So observe that weird switching of domain, codomain, and number of rows, number of columns. That's kind of uncomfortable, but that's just the nature of linear algebra. Here we call this matrix A the standard matrix of T, but we'll talk a lot more about it in section 1.9, a week away from today after the exam. That matrix here has a special role because that's all it took to make the transformation immediately become linear. Let's highlight this. That's probably the bigger punchline. And I have something ungrammatical right here, apparently. Usually Microsoft will tell you, but never mind. They're not giving me any feedback on that. But let's take a look at our new situation. We are going from R2 into R3. That means the matrix we're looking at, its standard matrix, had better be of size 3 by 2. There we have it, 3 by 2, so that looks right. We want to know if T is linear, and it says, briefly explain. If this is an exam 2 question, that's basically my way of giving you a hint. You're not doing much here. You're just going to probably observe that it's defined with a standard matrix. That's all it would take to show it linearity. So for this one, if this was a real exam question on exam 2, I would just say, let's see here. Since T of x equals ax, T is linear with standard matrix A. And we've had it, folks. Our complete argument is done by this theorem here. Well, any questions with part A? Okay, kind of the fastest proof ever. That's kind of nice when it works out that way. And part B is now a really kind of strange question. It says, for what vector x in R2 does this equation hold? But it's a familiar problem in a certain sense, right? It's not too different than taking a linear equation and setting it to 5 and wondering what x satisfies that equation. we're doing the closest analogy we can do with the fact we're working in larger dimensional vector spaces. So that's essentially all we're really doing here on this problem. To start this off, well, first thing you might do is make a really quick substitution, if I can highlight that. T of x is defined to be a times x, and so we can immediately write down T of x equals 103 implies, let's take that standard matrix A right here, A times x equals 103. So we're just taking the transformation, putting in the standard matrix, and observe there's really nothing new here from what we've done in the prior sections. We've already done this problem. In week 1, we did this problem. The only thing that's essentially new in this section is the new terminology about linear transformations. But solving this, let's take a look at what we would have to do. It says for what x? That means we're looking for a solution, and that means we need reduced row echelon form. And that means also, well, reduced row echelon form of what? We're going for the augmented matrix from this matrix equation. So here's where our solution is going to start in earnest. We'll go matrix A, augment it with, oh, geez, what should we call this? I didn't think that completely through. Let me make this bracket a little bit bigger. Matrix A augmented with the right-hand side, 103, would look about like this. Let me do that without the vector bracket. We can use equality because we're writing in an equal matrix. Just throw in that matrix A. So this will be 0, 5, negative 1, 1, 5, 0. I feel like I should hit that with blue since we just substituted from there. Then augment with 103 like we did in the prior step. And now the row reduction can start at this stage. It's really not too bad of a reduction. Let's see. There's a lot of options on this one. You could say divide by -1 here, make it row 1. Divide by 5 here, make it row 1. Let's go maybe that route and see what happens. So I'm dividing by 5 in row 2, swapping it into row 1 to get 1, 1, 0. Let's take row 1 and make it row 2 now, 0, 1, 1. And no change on this one, -1, 0, 3. Next row operation, we're going to go for this element to eliminate. So let's copy in rows 1 and 2, 1, 1, 0, 0, 1, 1. Then add row 1 to row 3 to get 0, 1, 3. It looks like we're nearly there. We just have to pivot off this location, eliminate the entries above and below. Any questions to that stage so far? Okay, let me know if any of my numbers go sideways. It's super easy to do on a Thursday, I'd say, late at night. I'm going to copy in row 2 to start, 0, 1, 1. Now let's pivot off that and take -1 times row 2, add it to row 1. We'll get 1, 0, -1. Likewise, -1 times row 2 added to row 3 is going to give us 0, 0, 2. At this stage, we have to decide, is this consistent or inconsistent? Good call. It looks fine at the moment until you realize, wait, this has been augmented. We have a pivot in the rightmost column. If this was an exam question, and it probably will be, you might want to just double check, say, I guess I opened it twice, this one. We're in this situation where we have a pivot in the rightmost column. Our solution or our system is not consistent then. So here we'll say inconsistent. That's kind of surprising because if you write down an ordinary linear equation, you're expecting an answer to those things. But here, we didn't find one. Notice we're going from R2, the plane, into R3. These vectors are linearly independent, so we'll find out later that when we map into R2 into R3, we're mapping into a plane. So imagine this is the plane oriented in R3 somehow. Turns out the vector 1, 0, 3 lies above the plane. We got inconsistent. If it was consistent, it'd be right on the plane, and we would find exactly how to locate that thing. The right values right here would get us to that vector. But in this situation with inconsistent, we missed the plane, and so we'll say, for this question, for what x in R2 does this hold? There is no such x. Just to make sure we actually answered that end question right there. Well, kind of a weird problem, but again, this is something we solved in weeks 1 and weeks 2. It's a review problem in a real sense. Any questions at all, folks, on getting through this one? Okay, let's take a look at just some more practice problems with transformations. You'll notice that this section is kind of tricky in a certain sense, but a lot of the problems are pretty much just review problems. Not this one, though. This one is all into itself. This is the new content. It says assume T, which maps from R2 to R2, is linear. These kinds of transformations are exceptionally special. You're going from the same dimensional space into the same dimensional space. Sometimes these are called linear operators. Our author just keeps it linear transformation. And now it tells us that it maps x to 4, 1, maps y to -1, 0. Evaluate that. It's all very cryptic because of the language. So when you see this, maps x to 4, 1, all they're really telling you is that t of x is 4, 1. When it says maps y to -1, 0, they're just in a very roundabout way saying t of y equals -1, 0. Me personally, I like symbols. I'd rather it be indicated this way each and every single time, but this is common in the discipline, so we have to see it from both different kinds of ways. One thing that I'm going to get in a very good habit of doing, and I did for exam 1, is the wording that you see here, I'm very, very consistent with it, and so is the author. So if I ask this question again, it'll be essentially in the same exact wording. You'll be wanting to pay attention to this and this are the keywords. So we need to evaluate t of 2x plus 5y, and sometimes there are options. You would take by order of operations, just do the scalar multiplications, the vector addition, and then do the mapping t. Except we don't know very much about the mapping t, right? There's not too much given to us. We don't even know what the vector x and the vector y is. If there's one thing we haven't used that will still help us. Anyone spot the one keyword there that's actually going to allow us to calculate that? There's just one word in there that's special where if we actually deleted that word, this really is impossible with the given information. Something around here. Good call, folks. It's the fact it said linear. When you get that information, that's always a good time because it means you now have a bunch of properties at your disposal that you can use right away. Let's just make a big deal out of that one as well. Being told you have a linear transformation now says, let's go grab those properties. You can do this. So let's take advantage of all of these all at once. Now these properties can combine. Our author would call it the principle of superposition. You can in fact just do this. T of, this just feels a little too big, let's fix that. You can take T of Cu plus dV, so U and V would be the vectors, C and D would be the scalars, and just simply write C times T of U plus D times T of V. This is our author's principle of superposition that he calls it, but it's just using both properties simultaneously for linearity. If you like, you can abuse that and use that here. It's absolutely a correct approach. But when you're studying linearity, it's sometimes a good idea to just go in stages and observe the properties as you use them. That's a good way to memorize the properties. So I'm going to take a longer approach and just write out T of 2x plus 5y to start. I'm completely forbidden from doing anything here because we don't know x nor y, but we'll use this additive property of linearity right here. This is the same as T of 2x plus T of 5y. Again, we call this operation preserving because the definition of that addition there, that is vector addition, could be different than the vector addition right there. Those could have totally different meanings based off the vector spaces they could have came from. But for us, it is the same operation. We're going from the same space to the same space. But it is kind of stunning to observe these don't have to be the same at all, yet linearity allows you to calculate in this way still. Then we'll use this property next, and we'll use it twice. We can, in a sense, factor out 2 and put it in front, and same with the 5. If we did that, we'd get 2 times t of x plus 5 times t of y. At this stage, we know what t of x is. We were told x maps to 4, 1, and y maps to -1, 0. We can just drop those in right here. That's a 4, 1, and that's a -1, 0. So we've used up all the properties of linearity, but it gets us to this stage. 2 by 4, 1, plus 5 rescaling. It says t of y, which is -1, 0. Then at this stage, it takes us definitely to a review problem in section 1.3, just doing the scalar multiplications and vector additions. So we're pretty much done at this point. We'll definitely finish it off though. Any questions at all, folks, though, using those 2 properties here and here?
I have a question. You take from one set space. So is this all the same?
Yeah, in this case, we're going from one vector space into the same exact vector space. So it's mapping into itself this time. And it could really be anything. This could go into R8. It could be all sorts of different stuff. And if it's linear, we can always break this up to get to that stage, was the bigger takeaway too. Other questions or comments so far? It would be, yes, absolutely. Well, you'd probably have to have 3 vectors here, like 4, 1, 0, -1, 0, 5, something like that. That's the only element that would change in this process. And Quentin asks, do we need to show the properties to get full credit on similar problems? I would say if you skip a few steps right here, you wouldn't lose credit. It's worthy to write this down since there's going to be times where we can't necessarily go from here to here just as fast. But yeah, if you did skip a few steps, I wouldn't take off points for that. I assume that you've done these kinds of things quite a lot before. Other questions so far?
You need to continue the.
Yes, absolutely. Yeah, we were just pausing with the properties, but we still have to finish it off, absolutely. Thanks for reminding me, though. I do sometimes forget to finish off a problem when we get into a discussion. That's a good reminder. Other questions so far before we finish this off? Okay, well, let's do the scalar multiplications to start. This is going to turn into 8, 2. Next vector will become -5, 0. Here's the vector addition property. We'll get 3, 2, adding up the corresponding entries. So at this stage, we did it, folks. Kind of a mysterious problem where we don't even know what x is, we don't know what y is, yet we can still do this. Only because of that one word there, giving us the right properties to make it happen. Any other questions so far, folks, on this one here?
No, it's what takes, I mean, it takes 4, the math that we took 4, 1, or it's a different.
It's some arbitrary vector in R2. We don't know what it is specifically. All we know is that the action of t on x, t mapping x, takes us to 4, 1. This is the only information we know about it. This question is pretty similar to the homework. And what they did do in the homework was they said what x is. That's kind of a distraction because it doesn't really help you out. It doesn't matter what x is. So watch out for that in the homework. You're really more concerned about where it's mapped to is what's important, not what x actually is in these kind of transformations. Again, that's pretty weird. But other questions so far? Okay, well, let's keep on looking at more weird stuff we can get into with transformations. So here we have a huge matrix, looks like it's 4 by 4. It says find all vectors x in R4 that are mapped into the 0 vector by the transformation X maps to A times X. I have to be completely honest with you. I hate that notation, but some people like it. Our author is one among us, among the people who like this notation. And so our author does use it here and there throughout the textbook. Not very often. It's maybe not the most favored notation of all, but here's what it's saying. This is just a shorthand for maps to. Let me write that out better. That symbol means maps to. So the more and more math you take, the more you'll see this kind of stuff here and there. But I'm more of a fan of function notation. Our author probably is too. He uses function notation more often than not. So if you see this, what you're always allowed to do, and sometimes it's encouraged, is just to say this is the same as T of X equals AX. T maps X into AX is just a different way we're indicating it. If we go this route. And we get even more information if we go this way. We now know that T as a mapping, it says for all X in R4. So it takes vectors in R4. When it's A times X, let's take a look at the dimensions. A is 4 by 4. X is 4 by 1. So if we look at these outer dimensions, the resulting product is of size 4 by 1 here to here. So that's the size of our codomain. So T maps R4 into R4. So that's our transformation T right here. We haven't even addressed the problem, and they want an answer in parametric vector form. But all we're doing is unpacking the notation. Sometimes that is the skill of mathematics, determining what they meant exactly with some weird new symbol when they throw them at us. Let's focus on this next. It says final X. Find all X that are mapped into the zero vector by this transformation. I'll focus on that notation there. So they're asking us, solve T of X equals 0. Just use gray to match up that color coding there. We're solving that equation altogether. It's not so bad because T of X, either you're using this notation, maps to AX, or this notation. Either way, you just make a substitution. AX equals the 0 vector. That means this problem is, I believe, coming from section 1.5 at this point. We're going to find the solution set to the homogeneous system of equations in matrix form, and we'll write our answer in parametric vector form. This is absolutely on exam 1. It'll be on exam 2, exam 3. This is a very common technique. So you could consider this problem to be pretty much mainly a review problem, with the only thing here being the new content, that one bit of new notation highlighted in yellow. Any questions at all, folks, before we start the process? Okay. Well, we have to remind ourselves, what is the process? Do we want reduced row echelon form, or do we want echelon form on this one? Anyone recall what would be the right strategy? Good call. This one is reduced. If you're doing anything parametric vector form, it's automatically reduced. We're solving for X. So we'll go reduced row echelon form is what's needed. Then we can augment our original matrix A with the 0 vector here from the right-hand side. And now this is when the row reduction is about to begin. Let's first put in A. It goes 3, 1, 0, 1, 2, 0, 1, 4, 10, 2, 2, 10. It's kind of a weird matrix. -6, -4, 3, and 8. Then, in this process, I almost always augment with a 0 vector. Even though nothing is going to happen on the rightmost column, it's just a good way for me to not lose track of the variables. So now, here's our setup. The numbers look kind of bad, but always can remember these are rigged numbers. Same on the exam. I ensure that they're going to come out right some way, somehow. So if it gets nasty on a real exam, that's almost a hint that maybe I made a small mistake somewhere on the row reduction. Something small, maybe a negative sign, could cause big problems down the line. But now that we're staring at this, We just have to decide what should our row one be. That's a pretty good one, and so is row two. Maybe we can swap those two and go from there. I'm going to swap both rows 1 and 2. So row 1 is now 1, 0, 2, -4, 0. Yeah, sorry, go ahead.
I have to know like which row is better to have at the first row.
That's a good question. It's kind of a pot shot sometimes. I would say sometimes if you have more zeros, that might be a good way to go, but that's not necessarily always going to work out. However, for these kinds of matrices, it usually doesn't matter too much which row you decide to go for. So it's going to be kind of a pot shot. Your algebra should be similar either way you go.
So, and anyway, we will get the same.
Yes, absolutely, absolutely. One thing that's kind of nice is the reduced row echelon form of the matrix is always unique. So even if someone takes a different process, all roads lead to Rome, essentially. We're going to land on the same exact matrix.
How about echelon form? Do we get the same exact?
We do, absolutely. The reduced row echelon form gives us the same exact answer, no matter what approach we took.
Is it the same for echelon form or?
Not for echelon form. Echelon form is special. Like if you do say, this is a good question. So let's take a really quick echelon form. Let's say it's 1, 4, 7, 0, 2, 3, 0, 0, 6. So just some generic matrix, right? It's definitely an echelon form, and it was row reduced from something. But you know what you could do is you could say double row 2. 1, 4, 7, 0, 4, 6, 0, 0, 6. This is also an echelon form, just as good as the prior one. So these are non-unique echelon forms, but the reduced row echelon form would always come out the same. We wouldn't want to double a row. We would want to divide by 2, forcing a 1 right here. We're all just going to end up in the same spot. Does that make sense with that question so far? Awesome. And that's a really good problem with echelon form itself. There is infinitely many different echelon forms. It does reveal the pivots, so if that's all you needed, we aren't worried too much about having different answers in that case. Well, it looks like we decided to take our row 2 as our row 1. I'd say anyone in the class feeling adventurous, try making your row 4 your row 1 and see how it lands. We should get the same exact thing. And it's the same with all these rows. There's a lot of ways to rearrange 4 different rows, for example. I just decided I'm going to put this one as row 2. So 3, 2, 10, -6, 0. So I swapped just the first 2 rows. For the rest, I'm just going to copy them in as they are. So 0, 1, 2, 3, 0. Then 1, 4, 10, 8, and 0. So there's our rearrangement. First pivot position is here, and we need to eliminate these values down below, the 3 and the 1. So let's copy in row 1, 1, 0, 2, -4, 0. Then the operation is going to be -3 times row 1 added to row 2 to give 0. No change here, so 2. -6 plus 10 for a 4. +12 minus 6 for a 6. And a 0. That look right to folks so far? Okay, now next operation, to eliminate that 1, just take -1 times row 1, add it to the bottom row. Now, maybe before I do that, let me copy in this row, just so I don't just delete a row by accident. 0, 1, 2, 3, 0. Okay, now it's definitely not going to be missed out. So -1 times here, added to the entry below, will give us 0. No change here, so copy 4. This will be -2 plus 10 for an 8. +4 plus 8 for a 12. And then 0. So here's where it is. We have a pivot position here, completely all set up. That's our next pivot. We have a 0 above, so that's nice. We just have to eliminate entries below. So the 1 and the 4 have to go. But you know, before I would do any of that, we are going for reduced row echelon form, which means that does need to be a 1. That might be the better operation. Let's just divide by 2 in that row, and then worry about the other stuff. So row one is going to stay the way it is, 1, 0, 2. -4, 0. I need to find a way to write a little bit smaller. These really take up a lot of space. This row we're dividing by 2, so it's going to be 0, 1, 2, 3, 0. Notice this row is the same, 0, 1, 2, 3, 0. If you have a duplicate row, here's a shortcut you can take immediately. This is just gone. You could just put in zeros right now if you wanted to, and that's a fine shortcut to take. This one we can divide by 4, and we get 0, 1, 2, 3, another duplicated row. So that's the surprise in this system. No matter how you rearranged it, you're going to see this kind of stuff. And row 3, row 4, if you put in zeros right now, that's a fine shortcut to take. To make notes more readable, I'll always take this additional step. So here's the copying portion. Row 1 is the same, 1, 0, 2, -4, 0. Row 2 will stay the same, 0, 1, 2, 3, 0. And now everything else is zeros. In a large extent, linear algebra is the pursuit of zeros in your matrix. So this is looking really nice. 0, 0, 0, 0, 0, and then another 0 row. We augmented right here. And let's bring in the variables. They are x1 through x4. But not all variables are created equal. X1 is a pivot column, or X1 corresponds to a pivot column. Next one is X2, which corresponds to a pivot column. But that means X3, X4, those are the free variables. When we go to write out parametric vector form, it's going to be X3 times a column vector, and then X4 times another column vector. So that's where our expectation is so far. This one might extend a little bit further. Let's get some white space going. Now for the next step, you can take some shortcuts here. You can think of this as an equality sign. So this is x1 plus 2x3 minus 4x4 equals 0. If you visualize it that way, you might as well solve the equation right here. So let me know how this goes. Row 1, I would read out and solve at the same time and write x1 equals -2x3 plus 4x4. We're just swapping the signs of those coefficients because of the equation solving. On row 2, let's do the same thing. x2 equals -2x3 minus 3x4. Then the last thing we'll say is, you might say x3, x4 is free, but sometimes it's better organized like this. If x3 is free, there's no restrictions on that, the equation we're about to write, and this is what no restrictions looks like. x3 is x3. Likewise, x4 equals x4. And now we have an array of coefficients belonging to x3, -2, -2, 1, 0. Likewise, coefficients belonging to x4 are 4, -3, 0, 1. We pull those coefficients and we're just going to write out the system, or excuse me, the solution in parametric form. So x is going to be equal to, maybe circle these. I think is an important feature of the problem. Those are the free variables. And so they form part of our answer. So it's going to be x3 multiplying a column vector plus the other free variable, x4, multiplying the next column vector. And in linear algebra, the column vectors are what's really important. So when we write things out in parametric vector form, part of that is for the purpose of showing these columns, which can be many different things in linear algebra. We'll see in chapter 4. Next, we pull coefficients. For x3, take -2. -2, 1, 0. x4, we're taking 4, -3. Let's double check. It looks like 0 there. And then a 1. You might add an extra statement. It's worthy if you decide to do it, but it's no harm if you don't. I wouldn't take off points. But it's good to remind ourselves, if we're doing parametric vector form, what was the parameter? It's the free variables. So we can say where x3, x4 are in R, which means we're also looking at a spanning set. This is a linear combination. We made it generic. So this is, if we span this column and this column, we are mapping back to the zero vector. Easy to forget the original problem. We just found all vectors x such that if we do this action, x maps to ax, or t of x equals ax in a different notation, same mapping, then these are the vectors that take us to the zero vector. We're going to later call, if you are into previews, if you're not, you can completely ignore this. But this problem is a chapter 4 problem. Later on, we're going to say the null space of A is span -2, -2, 1, 0, comma 4, -3, 0, 1. So when we define null space, it's really just this, solving that system right there. And what we're after is a spanning set for the null space. Null spaces eventually turn into, in chapter 5, eigenvectors. So that's a bigger concept that all this connects to. But for the moment, this is the review question you'll see on our first exam. Not this big of a matrix. Because it's an exam, I try to keep my matrices a little bit smaller, especially if there's a bunch of row reduction. This one is meant to be nice, but still takes a lot of time. Any questions at all, folks, on getting that process through? Okay, let's take a look. We've got 15 minutes. And maybe we'll put this one maybe here. A couple additional questions. We won't rush through them. We'll just see where we land. If we need to come back to this section after the exam, no worries at all. If we ever have to take extra time, the due dates that we post here, they also revise as well. So think of these due dates as being never firm until the day we actually finish the section. Then it becomes a firm due date. So here's our next problem. It says, let x be x1, x2. v1 is that vector, v2 is this next one. T is another transformation going from R2 back into itself, or from R2 into R2. We're told it's linear, so that's good information. It maps x into that, is what they tell us next. So a generic vector x, x1, x2, becomes a linear combination of those two supplied vectors. So let me tell you what this one is really all about. We want to find a matrix A such that t of x equals ax, but here's the bigger analogy. Imagine you're working in the plane and you had some line that you're interested in. In linear algebra, lines that we care about the most go through the origin, so I'll draw it that way. And if you want to find the equation, y equals mx plus b, you only need 2 points on that line. 2 points is enough information to make that happen. That's not always true for linear transformations, but if your vector space is of dimension 2, it is true. You just need 2 vectors. You need to know how they map. Here's how they map. And that's enough for us to specify everything about the linear transformation T. We can come up with that formula, come up with its standard matrix just based off this information, which is the same of grabbing 2 points and coming up with y equals mx plus b. So there are some analogies between these linear equations and what we're doing, but sometimes those connections are kind of thin. It's good to keep that in mind. Linear transformations really are, in other main ways, it's much its own thing. But if you can see a connection, it helps out. So the whole question is, find that standard matrix A such that t of x equals ax for all x, for each x. The way we can start is this right here. X maps into that thing means t of x equals x1 v1 plus x2 v2. To me, that's the hardest part of the problem, where if we're not familiar with what it means for something to map x into something, we wouldn't know that's equations on the background, and makes the whole problem just a little bit tougher, not knowing that information. But that's really our starting point. I would begin this problem by writing out with a more official looking pen, t of x. This x here is just a x1, x2, maps into the linear combination x1, v1 plus x2, v2. Now here's where we can pause for just a moment. A linear combination like that is the result of a matrix times a vector. Here's the matrix, v1, v2. And here's the vector, x1, x2, the original vector x. If we expand out this, all we're really doing is making a substitution from here to here. And that's a really bad color coding. Give me 1 second to fix that. We're going for a standard matrix, so this might be giving away the punchline, but that's worthy to keep the color coding right. Next step we'll take is, here we're just going to substitute. I write in -3, 5, 7, -2, times x1, x2, and we're pretty much done. We just have to state our conclusion. We'll say that A equals -3, 5, 7, -2 is the standard matrix of T. Kind of neat in a way, because now that you have this, you can do any kind of mapping. Pick any vector in R2 you like. We can now map that into its true actual output, because we knew the output of just 2 vectors right here going into that linear transformation is enough to specify the entire transformation. So we have a formula. In other words, let's put this maybe right here. T of x is now equal to ax for all x in R2. So just like with working in lines in the planes, 2 points in the plane would specify your linear equation. For linear transformation, make sure you actually have linearity. 2 vectors with R2 right here is enough to specify our transformation. That was R3, we need 3 vectors to make all this work. But any questions at all, folks, with this one here? Okay, so all we had to do to come up with the standard matrix of A is just observe, this is the definition of a matrix times a vector. It turns into a linear combination. So we just reverse engineered that and exhibited the matrix. You can take a massive shortcut here. That's the foregone conclusion each and every time. But I encourage you to write this kind of stuff out because it connects the ideas of what we did prior, what we're doing currently. So it doesn't feel like you're memorizing a bunch of random tricks. You're memorizing the actual mechanics of the algebra, why that works that way. Well, I think we're just about done with these notes. Let's see what we're getting into next. Oh, the counter examples, that's right. One thing I did mention is, when it comes to linear transformations, we like to write our lines going through the origin a lot. And here's another idea of why that's a thought. Any linear transformation, this word here is extremely important, will always satisfy this property no matter what. And that's kind of cool in a way. A linear transformation takes a 0 vector. This 0 vector is not necessarily of the same size. It has n different components, all 0, but it will guarantee map it to a different 0 vector. This one is of size m by 1, so m0 is in this one. So that's a foregone conclusion always, if your transformation truly is linear. So example 7, this is the last one that's similar to the homework. They ask us, show that the transformation T, defined in this way, so we have our sideways notation, kind of jarring, is not linear. Really all you have to do is, if you decide to keep this notation, take T of the 0 vector. Let's keep it sideways just to give that notation some of its fair due. 0 vector here can now be written out as 0, 0. That's a comma, it looks like a face. The 2 zeros are only because T takes 2 inputs. Now come over here. It's not always a bad idea to just think of this as a reminder, although the values are the same. It's not super important this time. But that's the x1, the x2 value, going into x1 and x2 in those corresponding ways. Would have made a big difference if it was like a 1, 3. But that just turns into a 0. Over here, we get a 4. And over here, we get a 0. So we have 0, 4, 0. If we go up here, we can say this is not equal to 0, 0, 0. And so t is not linear. Deserves an exclamation mark because that is a pretty fast way to go. It's not the only way to solve this, but if you observe something that just looks a little bit off, it's missing a coefficient. It's like, where is the x2 and 4 times x2? That's the one thing that made it nonlinear. Linear transformations requires 4 times x1 or x2 to be right here to allow us to actually get to the 0 vector when we map correctly. So that's one thing that can go wrong. Definitely not a linear transformation here. Any questions at all about this one here, folks? Okay. Well, this one is really the last one for what I assigned in the homework. I have another one that I did want to do. So I think what we will do is take a little bit of extra time after the exam, finish off these notes. I had some problems I thought, personally, I think they're kind of fun. If we had extra time today, we might not come back to those, but if you look at these and decide they look pretty interesting, let me know. I'm not opposed to putting the solutions down on those. They're kind of fun problems, but they go a little bit beyond what we're doing in the course. So we'll come back to this one after the exam, and I think then this is about a good stopping point. Any questions or comments at all, folks, about what we've done so far today or anything at all? Okay, well, let's call it at 6:41 officially today. Have a great weekend, folks. And if you have any questions while you're working over the weekend, don't hesitate to write. I'll be happy to help out.
That's my, good question.
Yeah.
Always recommend. Next one, chapters.
Those are all going to be a really good idea. Reading the chapter, doing those examples are a great way to go. You can also take a look at the sample exam one problems right here. They're not new. They're the problems that we solved ourselves, but they're still good problems, and they're written in a way to be kind of like a worksheet now. You can just scroll them. If you can still solve these problems, I base my exams off these notes and the homework problems. And then the other way you could review is, these are all brand new problems. It says sample final exam problems, but might as well just put it down here. Here's our problems on a chapter by chapter basis for additional practice even still. And they do have solutions at the very bottom. Yeah, I'd say my exam is more similar to your homework and this document right here. The document on the bottom is still good stuff, but it starts to feel not exactly similar. Yes, absolutely. I've tried to do all my grading on the weekend. So when I grade over the weekend this time, I'm not just going to go for the ones that were due. Anything folks have sent me in, I'm going to grade it. If you send it to me digitally, I'll email it back to you. But if I have a hard copy, I'll also scan and email it back to you. So anything you send me in, I'll grade it. It'll have your feedback before the exam.
Thank you.
You betcha. You too, thanks.
There's just 1.5.
Let me double check. Section 1.5. Yeah, that's right. Is it Christian by chance? Yes. Here you go. I still have one more set that I need to get back to you, but I'll be scanning these over the weekend. So watch for your ISE email address.